Okay, well, thank you very much. So about, I don't know, 5 years ago, I had a birthday conference, and you know, at the dinner, you sort of spend a certain amount of time thanking all sorts of people, and amongst other things, it was finally time to say something nice to John. And so just as I was getting around to John, he gets up and goes and takes a phone call. So, you know, all that niceness was wasted. So I should maybe repeat myself and just say what a wonderful thing it's been over the years to have John as both a friend and collaborator. It's a very, probably one of the more difficult things for sort of steps in a career is this business when you just after your doctorate, when you're sort of stopping working on a problem that's been given to you and developing your own research and having a sort of a wise elder brother around is just been marvelous. So thank you. And of course, you know, little brothers, of course, being rather sort of disobedient and annoying. He's also been very good over the years at tolerating my quirks. So it's fitting that we're going to be talking about something that's joint with Semyon Femonov and John. And so the question basically is understanding for the other sort of classical groups, which, you know, come in an infinite series and therefore can be completed to some sort of big infinite dimensional thing. The analogous things of KP flows in the sort of A series sets, sort of GLN, in a geometric context. Now there's with these generalizations, which get named BKP and CKP and so on, it's clear that the people who, you know, wrote them down had some sort of notion of how it was linked to, you know, orthogonal or symplectic groups. But it was a very interesting exercise to make people like Johann and well, Krichever, but it's nice to sort of sit down and make the link explicit. So maybe I'll just start by saying what I'm going to make explicit by sort of reminding you for KP, the setup. So the first thing is you have a Hilbert space, which splits into two pieces, sort of positive frequency and negative frequency. So this is power series in Z or Laurent series, and we've got positive and negative bits. And you have a Grassmann manifold. This is Alasigo and Wilson, which is the set of subspaces commensurable with H plus. So in other words, the projection onto the positive piece is going to be a Fredholm operator and index.
You recognize the question?
Hello? Oh, hi, Stephen. So it's a Fredholm, and I'm just going to fix index to be 0. The negative one, the pi minus, is, I'll just say small. So it can be Hilbert Schmidt or trace class or whatever. The other actor in this game is a group gamma, which is an infinite dimensional abelian group. And it is just the set of these exponential quantities So the exponential of some TI, the TIs are parameters, Z is another parameter. So T sub I belong to C and Z belongs to C. And it'll act by multiplication on H, on elements of H, and so on the Grassmannian. And sort of a final widget is the determinant bundle, which really you want to think of its dual instead over the Grassmannian. So you've got a plane and you take its top exterior power. Now, of course, this is infinite dimensional, so it's a little bit tricky, but you can do it. So it's got a section sigma, which is non-zero precisely over the set of things that are projected isomorphically to H. So when the projection ceases to be an isomorphism, this section vanishes.
Big cell.
In other words, known as the big cell. You can build the tau function. I'll put gamma. Do I want gamma? Maybe not. Tau of GT basically takes this section, normalizes it in a way that I don't want to go into. And so the Grassmannian is a homogeneous space. You act on it by a group of element of this GL infinity, and you act then on this thing with this abelian group, and you get a function that depends on T, and G is sort of the initial value of this thing. And I'll just put normalized here. Okay, so that's the infinite dimensional setup. Maybe just mention algebraically one of the if you want quasi-periodic solutions to the KP hierarchy. You've got a Riemann surface. You've got a sort of baseline bundle. You're tensoring it with LT. You're basically just taking this gamma here and using it as a transition function in a sort of clever way. And you're allowing at some point an arbitrary order of poles. And that's the algebraic solutions. That you then evaluate the tau function on the flow. The flow here gets manifested by this T. So I'm just mentioning it because there's a CKP version. The other thing is in finite dimensions, which is sort of the model for this thing, all of this stuff. So if you take the Grassmannian of GKN, K planes and N space, you have a sort of natural sort of affine coordinate. So this is the equivalent of the big cell, where you represent an element of the Grassmannian, you normalize, so you've got a K by N vector. And the entries of this, so you normalize here in the A. If you could just use a parameterization, which is sort of has great redundancy, which is just to put a K by N matrix and take its columns and think of these as generating a plane. Okay, so the columns have to be independent. They'll generate a plane. Obviously, there's a whole sort of freedom here in choosing, it's choosing a basis in a plane. So on this big cell, you normalize a piece to be the identity matrix. Okay. The other thing that's a sort of major player in this thing is you have Plücker coordinates. So the Grassmannian of K and gets embedded into the projectivization of the kth exterior power of Cn. And you just take a basis. Here, take its top exterior power of the plane, and associate to that its exterior power. These things don't come for free. So you'll get, in other words, so if I take an element here and forget the projective factor, I can just represent it as a sum of EI was B, EI1 wedge, EI K. And these are the associated coordinates. So these I'll just call actually I use pi here, shouldn't I? I'm going to be consistent. A sort of key player in what I'm going to be talking about is these things come with a set of quadratic relations. In other words, if you're in this exterior product, an element doesn't necessarily represent a plane. It has to be has to be a sort of pure element, a wedge of things. And an arbitrary element in an arbitrary sum isn't a wedge of something. So thank you. So you have the Plücker relations. Which you can sort of write out. You can take a sort of seed multi-index with length less or equal to k minus 2. You'll take another set of indices, I1 to let's see, what is it, k minus 1 minus the length of I0. Okay. J1 to jk plus 1 minus length of I0. Okay. And the Plücker relation is going to be that 0 is equal to the sum s equals 1 to k plus 1 minus I0 minus 1 to the s.
I0 is L of I0. What is I0?
I0 is a multi-index.
No, the lowercase I.
Oh, L of I0, sorry.
Yeah.
There you go. Okay. S equals 1. Pi, put I0, I1, the last one, k minus 1 minus L of I0. Okay, this is giving you something of length k minus 1, so you want to add in another index, and you take it from here. And then in this one, you just put in I0 as the starter, and then remove JS. J, k plus 1 minus L, I0. Okay, so that is these are their quadratic relations. You've got k indices here, k indices there, so everything works. And of course, I'm taking all of these to be disjoint. So these things come with a natural length, right? So the length is just the number of monomials, the number of terms. And well, it lives in the interval 3 all the way up to, I guess, k plus 1. Depending on the length of I0. See, if you take I0 maximal length, then you've just got fewer terms here to sort of flip over. So if you take I0 length k minus 2, then they're just 3 terms. 3 terms is short. And these 3-term relations, quadratic, end up being used as recurrence relations, used as recurrence. And these octahedral relations. And the basic idea is you sort of take the terms in one of these 3-term things, and you sort of cleverly put them on a vertices of here an octahedron, which will be the faces of a cube. You've got a lattice, and you sort of propagate through the lattice with this thing, taking basically the five of the terms in this short relation as given, and then that will determine the last one, and you sort of just move your cubes out into space. So that's the recurrence, and the idea is this is somehow a discrete version of the
your space is the lattice is z to the power of 2, n to the power.
Sorry?
So the space that you're moving in is the lattice n to the power of k, right?
Yeah, or z to the power 3 here.
But
They just take the short ones.
no, but okay, but it's embedded in z to the in n to the
It'll be embedded into a bigger lattice, but we sort of get there eventually, yeah. But it's and one of the sort of key things when you go back to the KP relation is you've got the Hirota relations, which have they're protean. They have many shapes. So I'm going to take the one that so this is a van der Molen determinant.
You're writing the addition formula, not Hirota, that's equivalent.
Mm-hmm.
You are writing the addition formula, not Hirota, but it's equivalent.
Yeah. That's what well, yes, that's why I said it had many shapes.
many lives.
So this is this infinite dimensional vector of t's. This is the sort of way of shorthand for x1 squared over 2, x1 cubed over 3, etc. Okay. And that's the van der Molen. And so if you write it out, you'll get some minus 1 to the j zeta. I should have a zeta n here, I suppose. Zeta n of t x1 xn y j, so maybe a plus 1. Zeta n plus 1 of t y1 yj yn, and all of this is supposed to be 0. Now sort of look at the 2 and it's an obvious parallel, and indeed this, which is a sort of mild modification of the tau function, gets used to sort of write out solutions. So that's the setup in GLN or GL infinity. You've got finite dimensional Plücker relations that sort of mysteriously get transformed into Hirota relations in infinite dimensions. And these Hirota relations will enable you to solve these recurrences. So it's a scheme. Now it's kind of interesting. You see, these are relations for the coordinates of one plane. These, on the other hand, you're moving. And there's this sort of funny duality between looking at one Plücker coordinate for a family of planes, right? Which is what the tau function is, it's the basic Plücker coordinate. Or looking at all the Plücker coordinates of one plane. And that's a little sort of game that gets played in here, and it's often just sort of swept under. The Hirota relations can sort of be used to develop the Plücker relations and things like that. So it's a sort of interesting little feature. But the aim of what we were doing is to see there's a BKP, which I won't talk about, that's the orthogonal groups. But there's a CKP, which is for the sort of infinite dimensional version. So one n tends to infinity of things associated to SPNC. There are finite dimensional recurrences, which are a little bit more mysterious. They're quartic. They've got many terms. I was hoping to get here early enough to write them out on a board and sort of whip them out for you, but you might have to sit and be patient instead. The Keshev recurrences, and there's this sort of enrichment of this hexahedral, which is sort of comes up in work of Kenyon and P. Mantle. And so the question basically is, what is the geometry of all these? You've got this nice infinite dimensional geometry that sort of takes the finite dimensional stuff of Plücker coordinates and stretches it out into infinite dimensions. And so how does this work? Okay, so there's a basic eraser that is needed. There's a basic sort of element is what space are we working in? And of course, the Grassmannians are sort of the basic homogeneous spaces, special cases of flag manifolds for the A series groups. And if you go to the B or C series, you get, instead of just ordinary flags, you get isotropic flags. So spaces that are flags that are completely null with respect to the symmetric form. So here for the CKP, we're going to be looking at an isotropic Lagrangian, and we're going to be looking at the Lagrangian Grassmannian, which are the isotropic planes of maximal dimension. So maybe I'll just start with finite dimensions. So the space is the Lagrangian Grassmannian. So in other words, it's isotropic. N planes in C2n, which you basically think of as a sum of two spaces, Vn plus Vn star. So C2n is going to be Vn plus V. Maybe I'll put this. Vn star.
Isotropic means that
it's completely null.
Completely null. Okay.
Everything, any pair of vectors in this plane, pair to zero. So we'll have bases E1 to En and E1 star to En star. And the basic, the only non-zero, anything, all the E's pair to zero, all the E stars pair to zero, and the only non-zero relation is that EI, or pairing, is the EI EJ star is of course minus EJ star EI, and it's the Kronecker delta. Okay, so just the simplest possible pairing. So that's our space, and now we have to think of it as sitting where. Okay, so we had that the ordinary Grassmannian was sitting in the nth exterior power, would have been C2n here. SPN is a smaller group than GL2n, and wedge n of C2n is not irreducible for SPN. So so it's be sitting in one of the irreducible components of wedge n C2n. So it's sitting inside, I'll just write wedge NN of, well, say C2N. So this is sitting inside wedge N of C2N. And what is this? It's the planes that are killed by the symplectic form, because you've got a skewed form. It's defined by this. So in other words, it's the set of omegas such that, so living here, but such that omega wedge some EI wedge EI star 0. Okay, so they're, in other words, they're n vectors. You wedge it, you get an n+2 vector. It's got to be 0.
That's the symplectic form.
That's a symplectic form, right? So now this has an interesting subspace, which is not a.
EI
The
star.
sum of the
Yeah.
star is the symplectic.
Not omega.
No, this is the set. These are this is an n form or an n vector, and you wedge it with this.
There's an implicit isomorphism between the space and the dual. So it's really an exterior two.
Yeah. Anyway, so there's going to be a. Oh yeah, I've used the letter V too many times, so I'll call it W. So an interesting space W sitting inside here. Should I call it W? I'll ask John.
What?
Are you still awake? Good.
Don't use W, use little W. Use little W.
No, I mean the subspace. What should I use?
Oh, well, we called it, I think lambda n0, but you can call it anything you like.
Okay.
Oh, the subspace of that.
No,
Yeah,
You want the image of what?
the principal minor space. What do you want to call it? Okay, I'll stick with W then. Okay. So what does this look like? Well, remember that in wedge n of Cn, C2n, the Plücker coordinates minors of and it should be the sort of n by n minors, right? So you take an n by n matrix in that, and you take its determinant. So you want a combination of these. So you write out a vector. It'll be these have these coefficients given by the minors, and well, what's the isotropic condition? Isotropy condition. This is for an arbitrary plane. It works out very simply. It's just A is symmetric. So that's very nice. In this setup, you've got right? You've got n rows here to choose some here, choose some there. And the ones you want for your subspace W will be obtained by choosing a principal minor up here and taking the complementary thing downstairs. So W will be the principal minors. Now, not of length n, because you're choosing the complementary set from this identity matrix of A. And but the correspondence, because the other one's just acting, it's just giving you a determinant that's 1 up to a sign. And so it'll just be the principal minor space. Okay, so there's this funny little space here. It's not an irreducible representation or anything. That's this thing, but it's sitting there. And it's sort of useful. Okay.
Maybe I could add a comment which would help those who are sort of following. What Jacques is picking out as W is the subspace of that irreducible S3 bundle, which in suitably ordered basis, in a sense, corresponds to symmetric partitions. Symmetric partitions, as everyone knows, or at least you've heard Alex describe, are those where the pairs of Frobenius indices are identical. Okay? And so you really only have one set of strictly ordered integers. And that is what labels the W. So if you count up the dimension, well, they'll tell you the dimension. But so that's not all the different coordinates. It's the subset corresponding to symmetric partitions.
Good, thank you, sir. So in any case, my Lagrangian Grassmannian will be sitting in here, embedded. And you can just sort of project backwards here. It will project with a sort of multi to 1 to this space. So there's a
Just a second. W is the collection of the principal minors?
yes.
Oh, okay.
Okay.
Or
I mean, there's still relations it satisfies over here, and that's precisely where these Kashayev things are going to come in. But anyway, so that's the
No, just the terminology here. Is W a collection of spaces? Is W a collection?
W. If you write out omega to be some things in here, right? You'll just think of it as sitting in here, Fi, Ei, satisfying this relation. Then and now the multi-indices, remember, they can either be starred or unstarred. So it'll be a sequence of there'll be starred things and unstarred things in there. And here will just be the multi-indices corresponding to the principal minors of A. So it'll be, in other words, writing it out, writing basis elements here. You'll get things like EI1, IK, and then in the complementary set of indices, so you in other words, you're taking the set of indices and indices which are either starred or unstarred, and in terms of their sort of enumeration 1 to n, the unstarred ones and the starred ones, if you put them together, give you all the numbers from 1 to n, but the set of indices here in this set is disjoint. Okay, I'll be writing it out later for 3 planes, because that's the sort of the key case.
it's a linear subspace, isn't it?
It's a linear subspace.
And those are the symmetric.
Okay. Okay, so they're sitting in this space. So the relations, remember, you still have You still have the Plücker, and you have also the linear relation, which given by some EI, which EI star equals 0. Right? That gives you a linear relation on the coordinates. Quadratic, linear. Okay. So I'm just going to do an example, which is isotropic three planes in C6. Okay. So the W coordinates, if you want. So in other words, I'm going to take an element of wedge 3 of C6. I'm going to write it, say, as F1, 2, 3, E1, wedge E2, wedge E3, plus F1 star, 2 star, 3 star, E1 star, wedge E2 star, wedge E3 star, and so on, right? So I've got the indices are either starred or unstarred, and you write out an arbitrary element. Okay, so what is the W coordinates, if you want? So the things corresponding to things living in here are F1, 2, 3. So I've just got unstarred, F1 star, 2 star, 3 star. But I've got each index appearing. F1, 2 star, 3 star, plus cyclic. F1, 2, 3 star, plus cyclic. With the obvious convention that when you put things in order, you have to sort of change signs and things. Okay, so you've got 3 of them here, you've got 3 of them here, you've got 1 there and 1 there. So you've got something that's 8 dimension. The non-W coordinates, well, you'll get things like F1, I don't know, 2, 2 star, F1, 3, 3 star. So you get repetitions in the indices. Okay, and so you're in 6 dimensions. So you'll have the short Plückers, three terms. You'll have Plückers of length 4, and that's it. Okay, and you have the linear constraint. Which tells you things like F1, 2, 2 star is minus F1, 3, 3 star, etc. Okay, so these get reduced somewhat. This is, I think, a 14-dimensional representation. So you get sort of 6. Once you put in your constraints, you get six things. And so what do? You take take the Plücker with the linear constraints, square, combine. So it's nothing terribly deep. But what you do is you eliminate the non-W coordinates. Okay, so you just get it into this space here. And you get basically the Kashayev recurrence. And because I think in interest of time, rather than so in other words, the Kashayev relation is basically just a combination of Klucker relations plus the constraint of isotropy. So I'm just going to say get Kashayev because I'm a bit short on time.
Can you just write down the general strength?
Well, okay, pi 1, 2, 3 squared pi 1 star 2 star 3 star squared plus pi 1, 2, 3 star squared pi 1 star 2 star 3 squared plus cyclic and 1, 2, 3. So there are 3 terms here. Is equal to 2 pi 1, 2, 3 pi 1 star 2 star 3 star pi 1, 2, 3 star. Yes, I'm trying to make him happy, but it's hard.
Known in the 19th century as the hyperdeterminant relation between Z2 cross Z2 cross Z2 type, and I think it is just written down by Haley.
Okay.
Are the relations satisfied by the principal minors of any symmetric matrix?
Okay. So those are the Kashayev relations, which need obviously to be written out. The hexahedron relations actually just involve the non-W hexahedron relations. Involve the non-W, if you want coordinates. But again, it's Klucker plus isotropy. So you're getting these relations. The isotropy is sorry, the hexahedron, the Kashayev relation. You're in an 8-dimensional space, you've got one relation, but you've got the projective relation too. So you're getting something 6-dimensional once you impose this constraint. And indeed, the Lagrangian isotropic space is 6-dimensional. So it's actually cutting things out. It's an image of a projection of the embedding from wedge NN. So it's several to one, but it's basically cutting it out. The hexahedron are living in wedge NN plus the Kashayev, and there it's cutting things out. Okay, so what's the sort of moral? You've got these relations. They're there on isotropic 3 planes and 6 space. By this sort of trick of adding in a seed generator, you can sort of shift them up and down. But they're essentially for these sort of 3-term relations on the general isotropic spaces and 4 terms. So how would you see that you want a theorem that says that short implies long? Right? Because these things still come with a Klucker relation. Remember, the sort of 3 and 4 Kluckers give you the Kashayev.
Well, I will ask a question. So, I mean, the Klucker relation, the ideal generated by Klucker relation cuts out exactly the Grassmannian, right?
Yeah.
Are these enough to cut out exactly the isotropic Grassmannian?
Up to finite ambiguity. They're square roots.
You are being ambiguous. Yeah.
Yes.
Yes.
Yeah, finitely ambiguous. Yes, which is better than usual.
Of the isotropic Grassmannian.
Okay.
It's not 1-to-1. It's not an embedding. It's embedding by a quotient by reflection. It's the embedding of the quotient of the isotropic Grassmannian. So it's actually an orbital. It's not a 1-to-1.
Anyway, so to see that short implies long, there's various things. There's this result of Oeding that does it for principal matrices. It's a little bit unclear there because it's saying basically the principal determinants. Once you impose all possible three-term or Kashayev relations on them, that it cuts out the full space. It only cuts it out set theoretically. So there's a multiplicity, but there's a nice, I like it anyway, geometric way of seeing this, which is that the following thing. If you just think of it, an n space sitting in Cn, okay, that's isotropic.
C2n.
C2n, sorry, thank you. You can intersect it with, say, the set where the first coordinate vanishes in C2n. And you'll get a, I don't know, let's call it V hat n, an n minus one space. I intersect it out, and then because it's you know, I want something isotropic, I want, I'll project out. So project out F1. Okay, so intersection projection. It's a symplectic thing, right? So symplectic reduction, intersect, project, etc. Okay, so do the same thing here. Intersection of F1 equals 0, pi F1 star. Okay, so you project out the other one, so you get another isotropic plane. It's not the same one. You can take the intersection of both and get something isotropic here. Okay. So what's the analog of this on forms? Okay, on forms, intersection is just the contraction. And projection is just projecting out the coordinate. Set coordinate to 0. Okay, so do that on a form. So you start out in sort of parallel with a form up here, and you'll get sort of things here. Now, the result is basically that if these correspond to isotropic planes, in other words, they satisfy the Plücker, plus coherence, projecting out not just the first coordinate, but all of them, so doing this for each one of them, then this one implies omega is also satisfies the Plücker plus isotropic. Okay, so in other words, you restrict the planes, you make sure that the results match in the way that is given by the thing that you want, and then the result is you can sort of glue everything together and get a thing. Now, this is dropping one dimension. The point is you can drop all your way down to 3 dimensions in 6 spaces. So you've got a huge sort of lattice of ways of doing it. Now, what happens is that the Plücker coordinates, basically under these operations, the Plücker coordinates, the Plücker relations that survive are the short ones. The others die, they disappear. So in other words, under these restrictions, you get down to something that it just has the requisite Plücker relations in 3-6 dimensions. And you've seen that they sort of, the results fit together back into some global thing. You also see, by the way, what the genericity results you need is that these operations of contraction actually have to give you non-zero results. So as long as you have transversality, the thing works. It works without multiplicities, and it gives you the short implies long in this thing. Now, we already saw the shortest ones gave you the Kashayev and the hexakedron up to this finite ambiguity. In other words, if you've got all possible sort of for these projections and things, you've got all possible Kashayev relations, then the result is something isotropic. So viewed from the point of the recurrence, this sort of 3-term is coherent with the extra recurrences you could go off by branching in other directions, which is a sort of useful thing. Okay. Okay, so what's the in infinite dimensions now? So I'll have to be a little bit briefer. So basically, you're in with the isotropic, still with the same Hilbert space. You've got a skew form which takes two functions and takes the residue of the product of f of z, and the way you make it skew is you just put g of minus z here. Kind of neat. And so you get the infinite Grassmannian. Isotropic. Sort of GR, say Lagrangian infinity, sitting inside the standard one. So it just basically the same way. You just ask that the things be isotropic. The group gamma, well, you get a subgroup, gamma 0. And it'll just be the set of gamma t's. But now where all the even t's are set to 0. So will be the e to the sum over I, p 2i minus 1, z to the 2i minus 1. Okay. Now, why does this preserve the symplectic form? So if you're starting out with something null, the easiest way is just to do the sort of Lie theory, you know, the not the calculation for the group, so the Lie algebra, and it's basically just the fact that if you have f of z, the residue of f of z and g minus of z is 0. If I'm taking the residue of z to the 2i minus 1, f of z, g of z, plus f of z minus z to the 2i minus 1, g of minus z, that's also 0. Okay, so it's on the level of the algebra, so it amounts to that, and then so this group preserves the thing. So you just got these things, the same tau function, just restricted. Algebraically, it's kind of amusing. You get algebraic curves that have an involution, and instead of looking at the instead of looking at the Jacobian, you just take flows basically along a suitable prim variety. So but it fits. It's coherent with this picture on the with gamma. So just finish with the discrete flows here. I think a lot of credit is due to Semyon, who really sort of wrote this out in a beautiful way, which is that you basically take the tau function, you shift it, but you have to put in these sort of corrective factors. So I'll just write out the one. So I'm going to choose, my ingredients are what? Discrete shifts, xi and yi using the, or just yi actually. I'm taking the flows just to be the odd ones. In other words, only the corresponding to this, the gamma zero up there. I define sort of shifted functions like this, yi minus yj. Ni minus 1, ni plus ni, and I minus j, or minus j, sorry. Product to infinity, ij equals 1. I'll just finish this, writing this out, and minus I must improve my handwriting.
Yeah, if he's doing that, I'll say a comment on what he's doing. He's just like in the KP case, he's evaluating the tau with some normalization, which is wise. He's evaluating it on an infinite lattice, so it's special values. It's not the Flickr coordinates; it's the values of the tau. But Mirablis, he will show that they satisfy the same articulations as those Gashaya from the X-Legion relation that Flickr coordinates.
Okay.
They're not the Flickr.
There we go. So we're shifting by sort of y and minus y, so that sort of keeps us in this t prime thing. We've got all these corrective factors here, and the way basically Semyon phrased it is this allows you to define a morphism from the ring of the infinite Grassmannian. To the ring corresponding to basically Z infinity. So these are infinite dimensional rings. And this formulation has a great virtue of giving you, you've got tau functions that are formal series, works here. You've got all sorts of things. So it's a very clever way of saying it, and it has hidden in it precisely this duality that John just mentioned, which is that, okay, we're flowing on the Grassmannian, but what this is saying basically is that we're getting the relations per point. So it's kind of odd, really. But that is what the discrete flow is, because you on the maps on the rings, you sort of turn it this way. If you're thinking of it as maps of points, things flip around. And so we've got this infinite dimensional lattice. And it's obviously just these shifts. So if you want, on the Grassmannian, the shifts are nice. It's a group action. On the lifting to actual functions, you've got all these weird corrective factors that come in as little twists and things. So it doesn't lift to a group action because of these correction factors. And that, well, sort of, I think it's time you had a break.
Thank you, Jacques. Other questions? Many questions.
So I have a question. So you also refer to this work by Hirschfeld abroad
Yeah.
And they have this tau function which is the square root of this.
I was scared that you'd ask us about that. We have no idea what the hell.
There's no geometric meaning. But
No, we sort of what you see. The trouble is, of course, you keep thinking, "Oh, damn, spinners! Oh no, doesn't work because there are no spinners for the symplectic group, right?"
Mhm.
So you'd have this square root, everything would fit nicely, and nah. So it's just sitting there. Now maybe there's some infinite dimensional artifact where somehow spin and SO are the same, or I don't
Even
know.
if you look at the solution, right, in the polynomial solution, that's all right, right, then you see that the polynomial is definitely not a square. So if you take the square root, you get something, so weird.
Yeah. So yeah, I no idea. Yeah,
So, but I could I say
Yes.
something?
sure.
We didn't use the square root business, and we think that's bonkers, right? It's not an actual thing. But a very nice criterion of Fisher and the Roden, they gave it. The question is which KP delta functions are secret or give you the secret. And they're okay. There are various, and you know that there are various simpler criteria for saying, okay, here's the KP delta function. When is it there's a KP delta function, when is it CPT? In particular, you only look at the odd floor vector. Again, that doesn't make it CPT. And they gave a very nice critical point criterion, which was that actually all they gave was that the derivative of the tau function, of the KP tau function, with respect to the even flow variables at the points where they vanishes. So it's a sort of critical point condition. And that can very easily be translated into linear conditions, additional linear conditions on the Flickr coordinate. That we did. So the picture is that wrote in.
Yeah, but that simply means that you have this inclusion which says the even out t's to -1 and the same.
Okay, that's also so there are at
So
least
it's-
2 or 3 really easy ways to say what a tau function capability satisfies. And each of those can be put into a form which is either fermionic or in terms of the further linear constraints on the Flickr coordinates, and we did all that. So there are a whole bunch of equivalent criteria. But the square root business seems that
Yeah.
it's fiction. It doesn't exist.
Sorry, Alberto. Yeah.
I mean, since you're talking of square roots, go back just KDB. Are there any tau functions for the master symmetries of KDB? Or you have a class of rational solutions of the master symmetries of KDB? You may call them with other names. Virasoro flows, second flowing structure, that kind of thing. In that case, for a family of those, in the paper with Boltzmann, we do have what are in practice the tau functions. I mean, you can write the potential as the second derivative of the law of that thing. But they must be in special cases of something.
But for KDB, it's clear, right? Because this is if you change the times there, because this is what Alexander did. He showed that KDB belongs to PKB, and PKB is the square root of KDB.
Yeah, but
That's what I'm talking of the master symmetry.
Okay.
the W.
Yeah, maybe that's what it is.
So those are the extra symmetries of Orloff and Schiller.
Okay.
So as far as I know, those are very important, but they do not lead to Hirota by linear equations. They are symmetries of the Hirota equations, but they are not themselves as a dynamical system expressible in terms of Hirota, as far as I know. But they are very important in another sense. That's a big, still open question which we
So
discussed.
my question is really the tau functions that we have already, in the sense that they do for tau functions are supposed to and give you the potential to the right things in the proper way. They could be characters, some representations, or who knows what. Maybe the W start.
All that is true, but the role of the W's or the extra symmetries. They are very important, and there's some work to be done by your students. There's an unproved theorem of which there are many examples. If you look at their critical points, look at the points where they vanish, those mechanisms vanish. That each time they get a critical point, it gives you for the Baker, the associated Baker function, a differential equation in the spectral parameter. So you don't just have the KP or VKP or CKP flows, but as already pointed out in the original work of Jim Hall and company, they preserve the monodromy of, it's very often a rational system, but the monodromy of that equation, linear equation in the spectral parameter. And that is, roughly speaking, just scaling reduction. So they play the role of scaling reduction, or Virasoro reduction, or W algebra reduction. They're all reductions which give you a smaller manifold which is invariant. And they turn out to be exactly, but at least in many cases, to be exactly the familiar isomonodromic systems that are studied on their own merits. But nobody has, for instance, ever, ever derived all the Panova equations to be found that way. Well, not all. Yes, all of the Panova equations, if you go to multi-component KP. But the Schlesinger equations, which are the example par excellence of Fuchsian isomonodromic interventions, nobody has ever derived it as a extra symmetry reduction of the KP or multi-KP. It probably is true. Give it to your students.
I mean, you cover so much that there are one or two words that are directly connected with this. They certainly come from the bispectral problem. That's exactly what they are. We have these tau functions that we're trying to sell.
Yeah.
Certainly.
Speaking of selling it, all the formula come from this excellent book that is on sale outside on the front.
Spectral problem. That's exactly what they are. And they have isomonodromy problems. But they are, they're all written down. It's a question of identifying them as a special case, something else.
So you're saying that the bispectral
Bispectral problem has two family of large solutions. One has to do rational solutions, KDV, and then you find the usual power function. And then there are the rational solutions with the master symmetries, for which we have the power functions. This will be a special case of some.
Depends what you mean by that. Depends what you mean by tau function. You can have
Something that
functions that depend on
I told you correctly. I can write the potential as the second derivative, the log of that.
Okay.
In that sense, I call that a power function.
Bertrand has a broader definition. Everyone has a slightly different definition. I stick with the Kyoto school. So for me, tau function is what they define, and there are two types, but they overlap. One is isomonodromic, the other is isospectral, and they all satisfy Hirota bilinear equations. If they don't do that, they're not a tau function. They're not a duck.
That's a good suggestion. I mean, duck and the back. Yeah. Sure.
And if it's broken, you can always use duct tape.
And next, the person needs that one. Yeah.
Okay.
Any further question, comments? No.